Welcome, focus learners. Okay, so if you've ever been stuck in traffic behind one of those massive, multi-axle, all-terrain cranes, you know they're absolute mechanical monsters of the road. But have you ever actually stopped to think about the crazy physics required to make them work once they park? Well, welcome to today's explainer, because we're jumping right into deconstructive physics of the quote-unquote floating 100-ton crane. And just to put that massive number into perspective, 100 tons is roughly equivalent to lifting an entire space shuttle, or, about 20 fully grown elephants straight up into the sky. It's a monumental task, and it requires some truly profound engineering.
Which brings us to an obvious question. How exactly does a skinny metal arm lift 100 tons without snapping? It's a genuine visual absurdity when you really pause to think about it. When these giants actually get to work on a construction site, you might even notice that they sometimes lift their own wheels entirely off the ground. They are literally hovering, suspended in the air.
Now, to the untrained eye, seeing a machine of this sheer size just hovering above its tires looks like a multi-million-dollar disaster waiting to happen. Usually, if a multi-ton truck isn't resting on its wheels, something has gone catastrophically wrong. But in reality, what you're witnessing is a masterpiece of what we call industrial engineering storytelling. It looks like magic or maybe a massive mistake, but it's actually strict, unforgiving physics at play.
Okay, let's dive into this. Part 1. Stopping being a truck.
So, we've got to completely shatter a massive assumption right out of the gate here. The myth is that a crane's lifting power comes entirely from a massive engine. But the reality? The crane is actually a dynamic balance scale. Before a single kilogram is hoisted into the air, that multi-axle vehicle has to do something totally counterintuitive. It literally has to stop being a truck. You see, a standard truck suspension system is designed to absorb weight, to bounce over imperfections in the road. But that bouncy flexibility, that is the exact opposite of what you want when you're lifting a rigid, massive, high-stakes load. So those dozen or more wheels that distribute its weight on the highway, they become entirely useless the moment the heavy lifting begins.
Instead of relying on bouncy tires, we enter this rapid mechanical transformation using the stabilization system. First, the machine deploys 4 powerful hydraulic outriggers that extend outward from the chassis. Next, generating immense hydraulic pressure. We're talking thousands of psi here. Those hydraulic cylinders push down so hard against the earth that they literally lift the entire 100-ton truck chassis right off its tires. This creates a wide, incredibly stable footprint. But listen, the operator has to be surgically precise during this setup. If those outriggers aren't set on a perfectly reliable, compacted base, the whole rig can tip over in a heartbeat.
Which brings us to the next phase, the giant playground seesaw. Now, what's really interesting about this is the secret to the entire operation, the center of gravity. This is the exact pivot point of the lift. It's a concept shared very closely with aviation, actually, and it is absolutely crucial for keeping the entire rig upright. To really understand the physics here, I want you to think of the crane just like a giant playground seesaw.
On one side of that playground seesaw, you've got your massive 100-ton load. If the other side is empty, well, the crane simply tips over. No way around it. To fix this terrifying problem, engineers use what are essentially the silent partners of the lift, counterweights. On these massive cranes, you'll see huge slabs of steel or solid concrete stacked high at the rear to balance out that massive weight at the front. And what's wild is that these counterweights are usually so ridiculously heavy that the crane can't even legally drive with them on the highway. They literally have to be delivered to the job site by an entire fleet of separate transport trucks.
By stacking those counterweights, the operators are intentionally shifting the overall mass strictly to the rear. This deliberate action effectively locks that center of gravity safely between those 4 outrigger pads we talked about earlier. Geometrically speaking, this is the golden rule of crane operation. As long as the center of gravity stays perfectly inside that square footprint created by the outriggers, the crane simply cannot tip over. But if that mass isn't shifted properly, and the center of gravity breaches that square, the balance is lost, gravity takes over, and the whole machine goes down.
And that leads us to our most critical section, the danger of distance.
So the crucial point is, we have a massive, potentially catastrophic 100 tons hanging in the air. And the dynamics of that weight, they change drastically depending on exactly where it's positioned relative to the crane. In physics, we call this the moment arm. It's not just about the static weight of the object, it's about the weight multiplied by the distance from the pivot point.
So there are some hidden lift dangers out there dictated by the strict laws of physics. Sloped terrain and soft ground, right? Those are obvious threats to the outriggers. But the third point is kind of a silent killer, an increasing boom radius. The further that boom extends outward, the more leverage that 100-ton weight has against the body of the crane itself. To put it simply, moving 100 tons just 10 feet further away from the center of the crane exerts vastly more tipping force than having that exact same 100 tons suspended right next to it.
Because of that immense leverage, just a few extra meters of extension can easily turn a completely safe lift into a multi-million-dollar structural failure. This is exactly why operators are glued to their monitors, completely reliant on onboard computers called load moment indicators, or LMIs. These systems are constantly, obsessively calculating the physics, the weight, the radius, the boom angles, literally thousands of times a second. They aren't just looking at the raw tonnage. They are measuring the exact tipping force at every micro moment of the lift to ensure that center of gravity stays exactly where it belongs. And hey, let's not forget the physical structure actually holding that load up in the sky. As the load pulses, shifts, or maybe swings in the wind, the main lift cylinders at the base of the boom have to absorb enormous stress and dynamic shocks. The metal itself plays a huge role here too. These booms are forged from specialized high-tensile steel, which is engineered to bend and flex slightly under extreme load. Actually, scratch that, it has to flex. If the boom were perfectly rigid, those dynamic shocks would cause it to snap like a dry twig. Let me tell you, standing next to a telescoping or lattice-style boom while it manages these incredible forces, visibly flexing every single second, it is a truly humbling experience. You can literally feel the sheer power contained in the metal.
Finally, we reach our last phase, negotiating with gravity.
Let's move on and see how this builds to a safe conclusion. The floating crane safely becomes an independent truck once again through a really careful, reversed sequence. First, the heavy counterweights are systematically removed and loaded right back onto their separate transport vehicles. Then, the hydraulic outriggers are retracted back up into the chassis. And finally, all that massive weight is safely transferred back onto the vehicle's many axles so it can just drive away to the next site.
It really highlights a profound truth. Every heavy lift is a negotiation between gravity and structural integrity. It really is an absolutely profound concept. What these magnificent machines do, it isn't magic. It is exact, rigorous mathematical calculation and a deep, abiding respect for the laws of nature.
So, I'll leave you with this. If you were on a high-stakes job site dealing with these massive, terrifying forces, would you rather be the operator up in the cab with the joysticks, actually executing the lift? Or would you rather be the rigger down on the ground, carrying the immense responsibility of making sure those outriggers are perfectly level and secure? Something to think about the next time you see one of these heavy metal giants building our world. Thanks for joining today's Explainer, and keep learning.